In this section, we're going to look at equilibrium and delta G. Okay, reactions do not always go to completion. On this axis of this diagram, we have free energy, and then we have the concentrations of our reactants, and over here, our products. When we begin our reaction, we have only A and B in the reaction vessel. We make C and D until we reach a minimum value of G. The chemical equilibrium is equal to the concentration of C times the concentration of D divided by the concentrations of our reactants A and B. Now, when the products are favored, the chemical equilibrium is going to be greater than 1 because you have more products than you have reactants. When the reactants are favored, you get a chemical equilibrium that's less than 1 because you're getting more of the reactants. Delta G, I'm just going to put it up here, delta G is equal to minus RT natural log of the chemical equilibrium constant. All right, that's how those two things are related. When products are favored, we have a chemical equilibrium greater than 1 and a negative delta G. When reactants are favored, chemical equilibrium is less than 1 and delta G is positive. Okay? Per this reaction, we take the log of something less than 1. Okay. Let's look at some examples, and again, this is an excellent place for you to stop the video and make sure that you're getting the right answers on these. All right, so the first one, if we have a reaction, the delta G is positive, well, we know that that's not going to be spontaneous and that the reactants will be favored. Just the fact that we have a positive delta G. If the chemical equilibrium constant is less than 1, then we also know that the reactants will be favored. A reaction that's carried out at 298 degrees Kelvin, for which delta G is a positive number and delta S is also a positive number. Well, we can look at this and see that this is going to be temperature dependent. We're actually going to have to do the problem. We know that delta G is equal to delta H minus T delta S, and we can just fill in. We need to note that that's in kilojoules. So I'm going to just make it joules per mole minus the temperature, which is 298 Kelvin. And our delta S was positive 150. And this is joules, moles, Kelvin. We always want to keep track of our units. The kelvins cancel and we'll have joules per mole. And we'll get minus 11700 for our delta G. A negative delta G would indicate that this will go to the product side. An exothermic reaction, well, our delta H is negative. The positive value for delta S, well, that gives us, if we come back up to this reaction, this term will be negative. this term will also be negative, the negative of a positive number. So this will be spontaneous. An endothermic reaction, our delta G is going to be positive with a negative delta S. Well, we look up here at this reaction. This is a positive term, and the negative of a negative gives us this as a positive term. There's no way that delta G can be negative, and so this will be non-spontaneous. And being I'm doing spontaneous, but if it's not spontaneous, then the reactants are favored. Here, this was spontaneous, and so the products are favored.